Great. So what you are going to cover today, and I think the people who know me already, because multiple people have attended this webinar already multiple times. Just a brief about me. I'm co-founder and CEO of Techlands with EV industry from last 11 plus years. I worked with Mahindra, had worked in another startup for a year. I had my other startup which I founded for electric three-wheelers, and this is my third startup which I'm working on right? It's only in the automotive industry. Okay, one slide, 1 second. Okay, this agenda points, I don't know how it missed out. So it's interesting that what we're going to cover today. And this is the first webinar we're going to cover this pointers. We have never covered in any webinar, but this is, I think, is the 30th webinar which we're conducting today. Okay, over the last 1 year. And 1st of March, we completed our 1 year of operations also, right? So okay, people are thinking my voice is not audible. Okay, is it the case? My voice is not audible, or my voice not might be not well, but that is different thing. But is not audible. Can someone please confirm with this? I'm audible. Thank you very much. Okay, great. So what we're going to cover is what is SOC and SOC algorithms in brief. We'll see what is Coulomb counting also in brief, and then we'll jump on the AI, ML, and DS overview. What is AI, ML? Because before we start understanding the SOC estimation bias and ML model, you should have some overview of what is AI, ML, right? And today I'll show the coding to you also. I'll run a code. I'll show the complete code to you, how the SOC estimation by the ML model happens and practice, right? And then I'll talk about some industrial applications also of this and the digital twins and AI in the industry. I'll give you some examples how the AI revolutionizing not only the algorithm part of it, also design part of it, right? So, do you feel excited about this? Just give me yes about the content of today's session. How many people are feeling this is good content? You know, I'm very interactive person. Unless I get something from all of you, I'll not be moving forward. You know that very well if you attended my previous sessions, right? So yes, no also is okay, right? Uh, right. So what is SOC? I think most of you know that SOC is just estimation or measurement on the actual charge levels of the battery pack of the cell, I would say, in this scenario first, right? So when you have a cell which has a storage of charge, you want to estimate that charge how much is left, right? If you have attended a previous webinar and associate algorithms, you might have remember that SOC is not a direct quantity like volume in a glass, right? For suppose I have this bottle of water, so I can just measure this height and I can see that this water height is this much, the volume of the water inside this is much, like for suppose 200 ml or 300 ml, whatever it is. But it's not the case with your batteries. You cannot see that liquid or charge in a visual format, right? Because those are electrons. So you need to somewhere you need to have some methods to quantify whether how much energy is there inside a cell. So if you weigh a cell which is fully charged and weigh a cell which is fully discharged, do you think that you'll be able to quantify a difference in the weight of those cells? I'm not asking for electron level micro, because if someone knows the weight of an electron, does someone remember that from their physics? What is the weight of an electron? Anyone? No, right? So it's very tiny, right? So physically, you cannot measure any weight of the cell, or you cannot see physically from any kind of transparent glass or any volume meter how much my charge is filled. So you have associate estimation algorithm, not measurement algorithm, to measure that how much charge levels are left in that, right? So one of those algorithms is like multiple algorithms are there, right? So we have Coulomb counting, then where we measure the current, and based on the current, because that is dq by dt. Rahul is quantifying it. Rahul. Okay. Good, Rahul. Good memory is very strong. Okay. So if you see this, if you quantify that, right? So coming down that, so if you do the Coulomb counting, what we actually do it, we measure the current, and based on the current measurement, we quantify how much electrons has traveled, right? There are some pros and cons to it. We'll see those things as well. And then we have other methods like open circuit voltage, where you are just seeing, okay, if my voltage levels are less, that means my battery is less charged or discharged, right? Typically, your lead acid batteries, which you have seen, right? Typically, you do based on that only. Do you see that any in the traditional, your car or bike might be classical example, right? Rahul, please don't skip it on my screen. If someone does it, we'll get it, we'll remove those people because it's something we have to stop sharing screen. It does not work that way because we cannot remove this now. I have to stop sharing and then reshare it. The disturbance to the complete flow. So please next time don't do it. Okay. So what happens is, okay, I lost the flow. Okay, so I was saying that if you have seen your lead acid batteries, which are there in your cars and cars and bikes, right? So typically you don't have a BMS who can measure measure the current or something like that, right? In typical lead acid battery which we use in your home also, they generally do based on voltage only. So they just take the voltage level and say that okay, whether my battery is charged or discharged, right? Or how much it is charged or discharged. Then you have advanced technology, which are physics-based techniques or model-based techniques, where you use advanced algorithms like RC modeling along with the EKF models, and then you have uh, electrochemical models to quantify and implement the SOC estimation algorithm, right? And the topic of today is data-driven models, where you have neural network models and ML models. So you might be thinking, why these two are different things? What is the difference between neural network and ML model? We'll talk about it. Important thing is for these application where Coulomb counting is happening, you don't need much data, right? Here you need OCV SOC data. But if you talk about physics-based modeling, it's very intensive in terms of your parameters, right? You need to understand the people who are, some of the learners also have joined from our existing programs. They know how intensive the physics-based modeling can be and how many parameters are there, how many equations you have to solve to just make a proper model, right? Very intensive in terms of your test data for validation as well as the input parameters which are there. And then when you talk about the ML data driven modeling, the name itself calls for data. So it is very data intensive. It is very data heavy. So it's as good as if your data is not correct, the model will not be correct. So it's like garbage and garbage out, right? Let's see what happens in Coulomb counting. So what you see here over here, same thing is presented in this format. So actually, with respect to time, you just measure how much my current is going inside that, and based on that, you estimate, right? Disadvantage, which generally people know about it, there is a drift on the current sensors and all those things. Long-term accuracy issues are happening, right? And the SOC also changes with respect to temperature and discharge rate. So if you see this typical example, if I compare around minus 20 degrees into 40 degrees centigrade, right? For a given C rate for 0.05, right? You see this, I'm getting a capacity of 2.77 amp hour, right? But for a same C rate, my capacity at lower temperature is 2.47. But if my C rate is increased, which is 2C, right? If you see this 2.52 is my at 40 degrees centigrade, and this capacity becomes very, very less at higher rate at lower temperature because resistance goes very high. Right? Same thing is shown over here also. When you see this for different temperatures, the voltage curve changes as well as the capacity. So capacity is nothing but the area under the curve or something that you can see that. But if you see this is the capacity which you are getting, right? So this is for suppose your 2.77, but here if you see this, this is 1.22, right? So the capacity changes drastically with respect to your temperature, right? This is understood by all. So that means your typical Coulomb counting may not work properly, right? Because the Coulomb counter does not know whether you are operating at 20 degrees centigrade or 40 degrees centigrade, isn't it? Yes or no? Yes or no? The Coulomb counter does know that, right? So it does not know, right? Because when you are trying to measure this just by a Coulomb counting, right? So it will give you errors, isn't it? Right? So these things are there. So that's why the advanced level of algorithms are also required to measure the SOC accurately. Now, interestingly, there is something called SOC estimation by ML models, right? Now, when you talk about ML models, what is advantage of these things? If you see this, it was not just taking current into account, right? And it can be any parameter. The beauty of data-driven models is whatever thing you as a parameter which you think is important and you have a data for it, you can give that to the model without thinking about the physics of it, right? Any so like for suppose today you think my SOC depends on voltage, current, and temperature. Tomorrow you think that okay, my SOC is also important. My battery dimension is also important just for rough estimation, and my series parallel number is also important. You can put every parameter as an input and let model decide whether the parameter is good or bad for the SOC estimation. This is the beauty of ML models, that they are not bound by the limitation of physics. They just fit the thing as they see it, right? Are you getting it, team? Anyone? Are you getting this? So this is very important thing to understand that what is actually happening, right? Okay. Sorry, my health is so I make sometime cough in between. So excuse me for that. Okay. So let's understand what is this AI, ML, or DS at the first place, right? So people have heard about AI, ML, and LLMs, right? Chat GPT is everyone's favorite nowadays, any which ways. But what are these things at the first place? So if you talk about it, I'll start with LLMs, which you have already seen it, right? Which are using at Chat GPT, Gemini, Bird, whatever you are saying. These are called large language models. So there are something as your embedding techniques, and you have those embedding which work on the sentences, and then you start making the sense out of the sentences and the interrelation between the words. And these techniques use transformer models as a by default things, right? Because transformer is something very advanced level of thing, and then new techniques which are supporting a complete LLM ops, which are different thing. I'm not going in detail of LLMs right now. Okay. Now, this thing is a part of DL, which is deep learning. Now, deep learning is nothing but when you try to use the neural networks, right? That time you call deep learning. Why deep? Because you have number of neural network, new number of neural layers in the deep layers, deep learning, right? So those things, there are multiple things. There is something called uh, normal neural network model, CNN model, right? You have LSTM, you have RNN, you have transformer, everything comes under DL model. And under that, you have elements as a special category of model. Now, if you see a wider category, when you're trying to fit the model, right, just based on data, and you're trying to do either regression or classification, that falls under machine learning, right? So then the machine learns in very simple terms. Whatever is learning is something secondary. If machine is trying to differentiate between good or bad, or is trying to predict something, is simply as machine learning. So without and on a very higher level, right? So although machine has learned, it can predict your next word, right? It can predict whether the image has one person or not, but it still is a part of a wider terminology which is called machine learning. Are you getting this? So that's why this is a like it's a bigger classification. And when you talk about AI, everything which comes under the umbrella of application, which consists of computer science also, comes under the AI category. So I'm not saying computer science is AI, but everything which is automated in nature comes under the AI category. Your algorithms which are there, which your robot applications are there, some logics are there, under falls under artificial intelligence, and it can be any form of intelligence, right? Not only machine learning. Understand this very beautifully and understand the difference between this, right? So any kind of intelligence if you are trying to keep, not logics, when not very straightforward logic, it can be a Boolean logic also, right? Whenever trying to fit in any intelligence in the system, right, that falls under the AI category. Are you able to differentiate it now? Generally, people start with top and go bottom. I generally prefer starting with bottom because ChatGPT is very famous, so you can relate it very well, right? Are you able to quantify now? So when have you? I think, but the most common example you might have seen, even when the ChatGPT was not there, uh, in Gmail, when you were trying to type something, they used to predict the next word, right? You remember that? It started way back. I'm talking about started in 2020 or 2021. Do you know this thing? So in the Gmail itself, when you were typing long back, it was trying to predict your next word, isn't it? It does not fall under the very simple ML model. It's always category of this, but there's no regression involved. There's no classification involved as such. It's trying to predict your next word. It's based on LMMs. Are you getting it? So it's a very specific category of MLDL or AIs. Right. Now, coming back on the topic, right? So machine learning has different this one categories. We have supervised learning, unsupervised learning, reinforcement learnings, right? Then we have classification, regression, clustering, decision making, right? Then classification is just trying to say this is good or bad, this is false or true, right? Everything falls under the classification category. Regression is when you're trying to fit something in a linear format. That is called regression, right? And clustering, when you're trying to make a clusters of people. Now, if I try to make a cluster of people based on this, right? So, for suppose, if I send a poll to you, all of you, right? And then you fill some data, like, okay, working or student, are you liking this session, not liking this session? And randomly, I fit every data in the model. What it'll do is it will make 3, 4 clusters. So there might be some people who are working, liking the session, and they're interested in the battery in AI. Some people working, not liking the session, not interested in battery in AI. Some student might be there. So it may make the clusters by its own. So that is comes under clustering algorithm. Not of interest for today. We are only focusing on regression today, right? Then we have decision making that comes under reinforcement learning for autonomous vehicles and other things, robotic application, ROS applications and all. Not going there. So we'll focus on regression today. Okay. So far so good. Are you learning something new? Are you learning something new? Give me in the chat. It's otherwise too boring. Okay, great. Let's see a slightly more distance. So, what is regression at the first place? So, if I ask you, age of your all of you, and then height of all of you, right? Like for suppose I mention as age, and then I ask height, right? And you will give me an answer, all of you, and then if I plot this data, right, on a scale, on XY scale, like for suppose this is Y and this is X, do you think I'll get a relation like this? All of you, do you agree? Yes or no? So this is my age and this is height. If I plot the age of all of you with respect to, if I plot the height with respect to age for all of you, right? Maybe not all of you, because I should take consider the junior kids also, right? So that's why we can take the complete spectrum. Right now, it might be only the thing. So I have to consider some school children also, some other people also. So we have a better bandwidth only. If we take only this bandwidth, there will be too much of scatter, right? So we'll go to some randomly to any road and ask the children also, babies also. So Shreyas, please don't scribble on my screen. Okay. So do you think I'll be getting or will be getting this kind of scatter plot? Yes or no? So the you will see that heights are changing and increasing with respect to age, isn't it? Right? Linear graph. So it's a scatter plot. Still, it's not a graph. It's a scatter plot because we just plotted the data. We're not making any line out of it. Understand the difference between this. This is something very, very important, right? You just plot as a scatter plot and randomly put the things on this data. Linear graph is different thing. Okay. So we'll get some data like this. There'll be some variation, right? Some and sometime what may happen as the age grows up, right? You will find this the spectrum, the width is further high. Do you agree with me? So for suppose when you talk about 50 age, for suppose we take the data, the spectrum of height difference will be very high. Yes or no? Initially, the spectrum of height difference for a 1 year kid might be very less. Yes, right? No, right? So what happens when you're trying to fit a best fit line now, right, on this data? Yeah, I want to represent, can I get a single line which can represent this data to me in simple y equals to mx plus c? This is called linear regression. When I'm trying to understand the behavior of my height with respect to one single line, and there are two coefficients in this, m and c, which is called best fit line. So what you're trying to do is in the best fit line, you're trying to put a line which can satisfy all the points. And there are two methods of this. One is your least square method. Second thing is your gradient descent. So least square fit, what you're trying to do is you're trying to find the sum of errors between all the points. Like for suppose this is my best fit line, the red color line, right? And then you're trying to reduce the error, total error from all the points. That's called least square fit. And then you find a best fit line which can represent data. And then you get the coefficient m and c. It's as simple as that. Very, very simple as that. Right? When you go deeper, right, and you're trying to understand this is the thing which you want to represent, the answer might be no. Now, in our case, when we saw the SOC model, what we want to have, we have not a single variable, right? We have multiple variables. We have voltage, current, temperature, right? And average voltage and average current because you want to see over the time also how this is changed, not only the peak values, the duration also, because a peak can be a single thing, but if the that overall average value is also high, it also matters a lot. Now, the relationship between these variables and the SOC might not be just linear relationship. It can be quadratic, it can be power, it can be logarithmic relationships, right? So this is important. So the simple linear regression will not work, right? That's why if you see this, there are so many algorithms for regression also. So one of them is for suppose linear regression, neural network regression, support vector, decision tree, lasso, ridge. We have other algorithms also which are very good, which will call XGBoost. We have random forest. If you know about deep learning and all those things, or ML and all those things, you know about these things, right? Light GPM. I can go in depth of all this algorithm, but not required. So there are so many algorithms. But for our application, a simple linear regression will not work, right? So first of all, let us understand the data. So let me just show you how the data look like, right? Let me just show you once. I think data is also here. But before that, help me understand, are you enjoying it? Meanwhile, I'm opening the data set for you. Are you enjoying the session or getting bored? Because some people, so before we start on the hands-on, right, let me show you the data. Now, if you see this data, what I have done is, this is a huge data set, okay? And if you just count this, Can you count the number of rows? This is 6,69,957 rows of data points. It's huge data, right? So if I just plot this voltage, right? If you see this, the voltage, the band of voltage, what we have, because this is the huge data set, Excel may hang also, right? So it's changing from 4.2 to around 2.8 or something, right? Similarly, this data set consists of a very large set of your temperature points also, right? Where is it? Right. So if you see this data is from your minus 10 degrees centigrade up to 25 degrees centigrade, right? So data is not for 40 degrees centigrade in this scenario. So I'm not considering 40-degree points, right? So we are considering minus 10, 0, maybe 15 and 25. Right? So if you see this 10-degree, so these four sets are available. So 0-degree, you have some data point, 10-degree, you have some data point, 25 degrees, it has some data points, and then 10-degree data, minus 10-degree, some data points are there, right? So this data is available over here. Now, then we have current also. So let's see how much current is changing, right? So Excel generally tends to hang, right? So if you see this current, so we have current levels also. We have current for 5 minus 6, then up to I think 17 amps the current is there. Then we have around 12 amps current is also there. In between we have 5 6 amps also current in between, right? So now that means the data is pretty wide enough to cover not only single temperature, not only single voltage, multiple bands of your current, voltage and temperatures, right? And correspondingly you have the SOC. Now if I just try to plot the voltage versus SOC in a scatter plot, right? Let's see what am I getting. Okay, so if I just try to plot the SOC, okay, I think I should plot reverse. Let me just try to plot reverse thing, because then this is the typically you have seen, right? So SOC comes under the x-axis. If I just try to put a plot scatter over here, right? This graph may look similar, but may not look similar to you, right? Because what is happening, these data points, what they are telling me, that even though my SOC is changing, my voltage is not changing. But if you see this particular, the top, can you see envelope part of it, right? This top envelope is telling me at any given point of time when the SOC is 20% for suppose, this is not crossing this value, right? And so this gives me upper bound of my voltage levels. Can you see that? Yes or no? Are you understanding what I'm trying to say over here? Right? So this gives me the upper bound of the voltage level for given SOC percentage. Right? So that, but if you see this, can I say this is the right thing? Can I put a curve fitting line on this? The answer is no. Because for the same SOC value, I have so many voltage levels, isn't it? Can I do just a OCV SOC lookup for this? I cannot do it, no. Because for a same volt SOC level, so many voltage levels are present. So it's not possible, right? So rather, there's something I'm missing out over here, isn't it? So let's try to use Python for doing a ML algorithm on top of this, right? So let me share my screen and let me show you where is my Python. Okay. Just 1 second. Is my screen visible to all of you? Python, this is visible, right? So I'm just importing, so I'm not going in depth of this, but I'm just telling you some flow of this, right? So let me import my libraries which are required and whatever data set I just showed you, right? I'm trying to import. Let me close this also. So I don't want to put it, right? So, and I imported the data set. Let me just add some row over here, right? So let me just show you what I'm getting on this data set, right? So if you see this, the same data set which I've shown you, same thing is mentioned over here. So I'm reading the same data set which I just showed you over here, right? And if I ask to describe the data set, it is by same 6,69,000 rows, and I can get the mean value, minimum value, and all those things, right? I can skip these parts. So as a data point, I know that data has voltage, average current, average values, and the target variable is SOC. So these are my independent variables, and this is my target dependent variable, right? And then if I just do a test and split, if you know slightly about ML, right, you have to do test and split, and then I try to fit a XGBoost model on top of it, right? And I run this, but it will fit the ML algorithm. It will try to fit the algorithm with respect to grid search CV and all those things. In the interest of time, because it will take half an hour just to fit the model. Yesterday I did it and I was running this, right? So let me just uh, show the prepared model which I just ran. Same steps, there's no steps which are being changed, right? I think it's visible to you. Can you see the outputs over here? Is this part visible to you? Can just tell confirm me this grid search CV outputs, right? Now, if I just fit this, that tells me the curve fitting was done, right? And it was 64 fits were done. And then if I try to put the data point and I trying to find that what was my R square value, what's my test R square and what's my R square for the model itself. So if you see this, my R square on training data was 99.89, which is very high if you know about statics and all those things. And my mean square error was just 1.2, just 1.2. My MSE error is just 1.2. That means my model is performing extremely well, right? And if I just take a very small data point and try to predict that what's my actual SOC versus predicted SOC, if you see this, my let me zoom in slightly. I could have used the plotly also, just make it much more interactive, but okay, I forgot. Maybe next time I'll show you, right? So if you see this, the actual SOC is my blue color line and my predicted SOC is red color line. Do you think this model is doing a good job? What do you think? Is my model is good, right? Whatever my actual SOC is there, my predicted SOC is exactly overlapping with this with just 1.2% error, right? And actual Amrita is saying no. Amrita, why you're saying no? Some outliers you are saying that's why it can be overfitting. No, it is not overfitting, right? Overfitting, it's said, one second. Overfitting, why I'm saying it's not overfitting? Because I already divided test data and training data. If my overfitting was happening, my test score might be bad. Understand this. My training score was good, as well as my test score also was good, right? Are you getting this? So I can confidently say this is not overfitting. Understand this, right? That's why I showed you both the things. Okay. So that this model is pretty good. And it took just, I think yesterday when I ran this, it took around 25 minutes to run, and I reduced this hyperparameters and so I couldn't further reduce it because I wanted to do in hurry. So I just reduced the hyperparameters and all, right? So this is doing a pretty much good job. Now, interestingly, if I plot a scatter of this, right? If I just plot a scatter of this for predicted SOC versus actual SOC, you see this, there is a less spread of the SOC, predicted SOC at the higher SOC levels, but at lower SOC level, the spread is very high. Although my model error is too less, understand this very carefully. My model error is very less, is only 1.2%, right? 1.2, and my R square value is also pretty accurate, right? then why I'm getting so much spread for the actual SOC and predicted SOC for lower SOC, but I'm getting a lower spread for higher SOC? Anyone can want to answer that? They can unmute and answer also if you want to. Anyone? On the chat also, if you would like to just give an answer, give it. No one? Okay, let me go back to my presentation. So it's not that my model was wrong. It's not that my anything else was wrong. It's because of the physics which is there. The underlying physics was driving it. So what happens? What happens? By default, my OCV value, as I mentioned in the past, changes with respect to temperature, right? So with respect to temperature, my SOC value changes. If you see this, the SOV change with respect to different temperature at higher SOC level is less. But as my temperature as my temperature changes, so at lower SOC level, I have very high spread of OCV. Are you getting this? So the temperature impact on SOC is higher on the lower SOC bands than it is on higher SOC bands. So my algorithm was right. I just showed you the spread of predicted SOC because in the actual data itself, when you try to put it, you will find that the spread is too high. So the model was accurate. It was just telling you for a given predicted and actual condition, there is too high spread. And then we only took the data for minus and 25 degrees centigrade. We did not consider temperatures. Can you please go on mute? Other people. Okay. Are you finding this insightful? Give a poll. I have given a poll. Let me take this one. Are you finding this interesting? Nah, I'm not repeating it. Just kidding. Okay. So that means somewhere, my temperatures are playing a role, right? And those values are correct if I see in linear format. So that's why when you're trying to predict the time sensitive things, so you have to use time series databases. You have to use time series regression algorithms, right? The normal regression algorithms or classification algorithm may not perform well for a data which is time sensitive, right? So there's something time series forecasting and all those things. And I'm not going in detail of those things today, right? So that way your your predictions become much more accurate because then you consider the complete spread of it. And then if I would have given the data of higher temperatures, because in the data set we had only data for these 4 points, minus 10 to 25 degrees centigrade. If we had data for 45, 50 guys think that my prediction might have been very pretty much more accurate, right? Because this data itself was not there, so it was not able to understand that the way I said in the beginning. If I take a poll in this session and ask you, give me your uh, height versus age, right? So if I ask you your age versus height, right, and I try to plot this, I may get a very random data because in this session, I may not have the right spectrum of age, isn't it? Are you getting it? Because maybe the people are from 20 to 40, where the age changes, but the height is more or less static. Are you getting it? So I may not get a right fitting of this curve. Are you getting it? So that's the reason also when we put the data, it's very important the data is accurate and data has a spectrum of it. All the corner cases are covered in the data driven model. Otherwise, it will not give you anything. Good to go. Understood this, right? Shall we continue? Okay. Now, let's understand what is the application of this, right? Sorry for that. Just 1 second. Let's talk about the application of this. So, what happens when you're trying to understand the data perspective and trying to model this, right? There, all this data can be very useful, and you can have a digital twin which is working on this data points. And the model which you build is basically your digital twin. Are you getting it? So, like for suppose I built a model for SOC estimation, and I built a very lightweight model. I did not build a very heavy model for this demo, right? So that model can be in continuous sync with your battery pack data, and then can keep on continuously monitor whether my vehicle is performing well, if my SOC on the BMS is correct, not correct, and all those things can be done, right? Multiple things can be done. Similarly, the same uh, uh, thing can be done for different applications, like for modeling the battery pack, simulation and control, motor controller, and anything else, combustion. There's something called virtual sensors and all those things also, right? So the application of this is not only for SOC, it's going beyond that. So what are the other applications? The AI for cell manufacturing is very strong. So what happens in the production line of battery cells, right? There is a complete data which flows. So what is the material? What is the mixing ratios? What is the drying, coating and drying process? What's the electrode thickness while calendaring? What's the porosity? And people who know about physics-based modeling or who have done sessions with me, they know all these things in detail. So what is the assembly process, electrolyte fitting quantity, forming and testing process of that, EIS, resistance and all those things. And then you do a cell characterization. So in between you generate in the processes huge amount of data. What if I feed this data into the AI model? What will happen? Right? So the industry is already leveraging this. So recently, last year only, I think this came that LG has built this own AI model. So complete the cell design in 1 day, what they used to perform in 14 days. So earlier they used to do design proposal, performance analysis, and all those things. They built the model, AI model, on the data what they had, and that data was 1 lakh design cases. It's not a small data set, it's a huge data set. 1000 design cases. Understand this. That means there was 1 lakh designs or 1 million designs. No, sorry, point 0.1 million designs what they already had for the cells. It is something very, very important. They might not be having that many models in the market, but they might have done the iterations on different thickness, porosity, and sell different designs to make the iterations. So all those data, what they built, they saved it, and then they made a proprietary model on top of it, right? The AI model, and so that they could make the cell designs. Battery performance, yeah, it changes. We'll come back on this, right? So then if you just make a model, so you don't have to do all this performance analysis and all those things manually. Because typically what you used to do is you used to make coin cells, then pouch cell. Who people are from cell industry, they know this, the complete process. You design the particle size, do the electrochemical modeling, you do the simulations and understand whether the simulation is meeting my result. If simulations are meeting my results, then you make the coin cells, then pouch cell, and then cell integrals and test it out whether it is meeting the client requirement or not. But now, since you already have done in the past as a company, you have all those data with you. You can just build an AI model and then put the input data over here, what you require, and it tell you the optimized proposal. This is the power of AI in the engineering domain, right? This is all for our session. So I just like to give you brief about Techlands also. And did you like the session first of all, right? So Important thing is, one second. Okay, where is it? Right. So did you like the session? Help me understand the chat whether you like the session, this part of it. So did you know all these things first of all? Anyone would like to mention that? Did you know all these things? That's the application of these things, right? Then we'll talk about the things areas. In the chat, can someone mention me? Did you know all these things? That this application of in the cell and then BMS? Yes or no? Okay, good. Some people already knew that. Right. So these things are very pretty advanced, right? And it's not like that AI is not being used in this kind of application. It is being used in applications, right? And people are building on top of it, right? So just let me give a brief about Techlines also. So this is the old logo. I have to change the logo. Our new logo is this. So we are a ecosystem player, EV ecosystem. We have training programs, we have engineering services. We are conducting these kind of free webinars for the our community. So I think you might be joined via community what we have or join via some other channel references, right? So we are trying to build an ecosystem of EV around the globe. It's not only Indian ecosystem or something. We have customer clients from US, Canada, Germany, UK, and all those things, and our learners also there from different countries. Apart from that, we are startup registered in Karnataka, right? Me, Lokesh, and Vikram are the co-founder on this. We every one of us has more than 11 to 15 experience in the industry. We come from IIT background as alumni, so we are like focus on quality things. That is something like devil lies in detail. That's a philosophy we follow also, right? So you can join our community courses or this one.